AndueCore5 Project Description. The AndueCore5 is a fully custom-designed 5-bit computer architecture created inside the game No Man's Sky using only the available building components and logic systems within the game. The project represents an attempt to recreate the fundamental operation of a computer from the ground up by designing every major subsystem manually. Instead of starting with an existing processor and creating software for it, the AndueCore5 begins with the basic principles of digital logic and builds upward into a complete programmable machine. The project is not a visual representation of a computer, and it is not a decorative structure. It is a functioning computer system where each logical operation is physically created by interconnected hardware components. Every register, every memory location, every arithmetic operation, every control signal, and every instruction execution path exists as a real hardware structure inside the game environment. AndueCore5 operates entirely within the rules and limitations of No Man's Sky. The computer was constructed using the base building system and operates without glitches, exploits, or unintended game behavior. The entire machine was designed to function reliably while approaching the maximum allowed construction part limit of a base. Reaching this limit required careful planning and efficient use of every available component, because every individual logic element consumes part capacity. The final design demonstrates that a complex programmable computer can exist within the strict hardware limitations of the game environment. The goal of the project is not to create a computer that competes with modern processors in speed or capability. Instead, the goal is to understand and demonstrate the fundamental concepts that make all computers work. The AndueCore5 exposes the relationship between memory data movement, arithmetic control logic, and output. Every action performed by the processor can be traced back to a physical change in hardware state. The design philosophy of the AndueCore5 is based around simplicity, transparency, and modular construction. Each hardware component has a clear purpose. Each instruction performs a specific operation. Each data transfer follows a defined path. There are no hidden layers between the program and the hardware. When a program executes an instruction, the result is produced directly by the physical logic designed for that instruction. The architecture uses a 5-bit data system. Every piece of information inside the computer is represented using 5 binary values. This includes instructions, memory addresses, register values, arithmetic results, and display information. A 5-bit system allows 32 possible values, which is enough to create a functional computer while keeping the hardware manageable. The choice of a 5-bit architecture creates an interesting balance between simplicity and capability. A smaller system makes it easier to understand every individual operation while still allowing the computer to perform meaningful tasks. The processor can execute programs containing loops, decisions, calculations, graphics, animation, text display, and interactive applications. All binary data inside the AndueCore5 uses a little endian representation. Unlike the traditional way binary numbers are usually written, the least significant bit is located on the left side. This means the first position represents the value of 1, the second position represents the value of 2, the third position represents the value of 4, the fourth position represents the value of 8, and the fifth position represents the value of 16. This bit ordering is used throughout the entire architecture, including instructions, registers, memory, and display data. The central feature of the AndueCore5 architecture is the bus register. The bus register acts as the main highway for information inside the computer. Instead of every subsystem having direct connections to every other subsystem, all major data transfers pass through the bus. This greatly reduces hardware complexity while still allowing every part of the processor to communicate. The bus register connects the major components of the computer, including the red register, green register, arithmetic logic unit, program counter, stack memory, output register, data ROM, and display systems. Every instruction that moves information does so by controlling when a component places information onto the bus and when another component receives that information. The bus architecture also makes the operation of the computer easy to understand. At any moment, the programmer can determine what information is currently moving through the system and which hardware component is responsible for the next operation. This visibility is one of the most important design goals of the project. The processor is controlled through a standard fetch, decode, execute cycle. This cycle is the foundation of how the computer operates. During the fetch stage, the program counter identifies the current instruction location. The instruction stored at that location is read from memory. During the decode stage, the instruction is interpreted by the control logic. The decoder activates the specific control signals required for that instruction. During the execute stage, the selected hardware performs the operation. This may involve moving data between registers, performing an arithmetic calculation, accessing memory, changing the program counter, updating the display, or stopping the processor. After execution, the processor continues to the next instruction, unless a jump instruction changes the program flow. The program counter is one of the most important control components in the system. It determines the order in which instructions are executed. Under normal operation, the program counter advances through memory one instruction at a time. However, the AndueCore5 also supports several methods of changing execution flow. A program can directly load a new address into the program counter from the bus register. This creates a direct jump where the destination address is provided by the current data path. A program can also load a new address from data ROM. This creates an indirect jump where the destination address is stored in memory. Indirect jumps allow programs to create flexible loops and branching structures because the destination can be changed by modifying stored data rather than rewriting instructions. The processor also supports conditional jumps. These instructions allow the computer to make decisions based on the current state of the arithmetic logic unit. The two primary conditions are zero detection and overflow detection. Zero detection is used for comparison operations. By placing two values into the arithmetic logic unit and enabling subtraction mode, the processor can determine whether two values are equal. If the result of the subtraction is 0, then the values matched. This allows the processor to perform comparisons without needing a separate comparison circuit. Overflow detection is used when the arithmetic logic unit produces a carry beyond the available 5 bits. This allows programs to detect when a calculation exceeds the available range and branch to a different section of code. The architecture uses dedicated registers to store and process information. The red register and green register act as the primary working registers for arithmetic operations. The output register stores values intended for external display. The stack provides additional memory storage. The bus register provides temporary communication between all of these systems. Each register is built from simple digital logic principles and maintains its stored value until another instruction changes it. This allows the computer to preserve information across multiple instruction cycles and create complex behavior from simple operations. The AndueCore5 demonstrates that a complete computer does not require thousands or millions of components before it becomes meaningful. The fundamental concepts of computing exist even in a small architecture. Data storage, arithmetic, decision-making, memory access, and output are all present and working together. The project represents a physical exploration of computer science concepts, including processor design, instruction set architecture, digital logic, memory organization, and low-level programming. By constructing the machine inside no man's sky, the project adds another challenge, because every improvement must be balanced against the limited number of available building components. The result is a unique combination of engineering, programming, and creativity. The AndueCore5 is a computer built inside a game, but it demonstrates the same fundamental principles used by real computers. AndueCore5 hardware architecture and theory of operation. The internal hardware organization of the AndueCore5 is designed around the principle that every component should have a clear purpose, and every operation should be understandable by following the movement of information through the system. The processor is divided into several major subsystems that work together to create a complete programmable computer. These subsystems include the bus system, registers, arithmetic logic unit, memory system, stack system, program control system, random number generator, and display hardware. The bus register. The bus register is the central communication system of the AndueCore5. Almost every piece of information that moves through the computer passes through the bus. The bus register provides a single shared pathway between the different parts of the processor. The purpose of the bus architecture is to reduce the amount of direct connections required between components. Instead of every register and memory device needing a connection to every other device, each component only needs to communicate with the bus. This creates a simpler and more efficient hardware design. When a component needs to send information, it places its stored value onto the bus. When another component needs that information, an instruction activates the receiving hardware and the value is captured. After the transfer is completed, the bus is cleared when required by the receiving hardware. This design creates a controlled flow of information. The computer does not move data automatically. Every transfer happens because an instruction specifically activates the required hardware. This is a fundamental design principle of the AndueCore5. The red register. The red register is one of the two main working registers of the processor. It stores one of the input values used by the arithmetic logic unit. The red register receives information from the bus register through the load red instruction. When this instruction is executed, the current value stored in the bus register is copied into the red register. After the transfer is complete, the bus register is cleared. The red register keeps its value until another load red instruction changes it. This allows a program to store a value and use it later in calculations. The green register. The green register is the second primary working register connected to the arithmetic logic unit. The green register receives information from the bus register through the load green instruction. Similar to the red register, the bus value is copied into the register and the bus is cleared after the transfer. The green register also has an additional ability. It can copy its stored value back onto the bus without destroying the value inside the register. This is useful because a program can reuse the same stored value multiple times without needing to reload it from memory. Together, the red and green registers provide the arithmetic logic unit with two independent values. These two values form the foundation of calculations, comparisons, counters, and game logic. The arithmetic logic unit. The arithmetic logic unit is the calculation center of the AndueCore5. It is a 5-bit ripple carry adder designed to perform mathematical operations using the values stored in the red and green registers. The default operation of the arithmetic logic unit is addition. When the processor is in addition mode, the output represents the sum of the red register and green register values. The arithmetic logic unit can also perform subtraction. Instead of using a separate subtraction circuit, the processor uses a subtraction toggle. When subtraction mode is enabled, the arithmetic logic unit changes its behavior and calculates the difference between the two register values. This design reduces hardware complexity while providing both addition and subtraction capability. The arithmetic logic unit continuously produces an output. The result does not need to be stored before it can be evaluated. This allows the processor to use the arithmetic logic unit as both a calculator and a comparison system. The zero condition. The arithmetic logic unit contains zero detection logic. When every output bit of the arithmetic result is inactive, the zero condition becomes active. This condition is used by the jump if zero instruction. The zero condition allows the processor to compare values. A program can place one value into the red register and another value into the green register, enable subtraction mode, and check whether the result is zero. If the result is zero, both values were equal. This creates a hardware-based comparison system without requiring a dedicated compare instruction. The overflow condition. The arithmetic logic unit also produces an overflow condition. Overflow occurs when an addition produces a carry beyond the available 5-bit range. This signal is used by the jump if overflow instruction. Overflow allows programs to detect when a value exceeds the maximum range of the architecture. This can be used for counters, loops, mathematical operations, and game mechanics. The +1 operation. The AndueCore5 includes a +1 instruction that adds 1 to the current arithmetic result by enabling the carry input of the adder. This operation is especially useful for counters and incrementing values. Because it relies on the carry input system, it is designed for addition mode and is not intended to operate as a subtraction function. The output register. The output register provides a connection between the processor and external display systems. When the bus-to-output instruction is executed, the current bus value is copied into the output register. After the transfer is complete, the bus register is cleared. The output register acts as a final destination for processed information. Programs can use it to display values, control indicators, or provide output to other connected systems. The program counter. The program counter controls the sequence of execution. It stores the address of the current instruction being executed. During normal operation, the program counter advances through program memory. However, instructions can modify the program counter to create jumps. The program counter can receive a value from the bus register through the load program counter instruction. It can also receive a value directly from data ROM through the data ROM to program counter instruction. Conditional jumps use the arithmetic logic unit conditions to determine whether the program counter should change. This gives the processor the ability to create loops, decisions, and complex program structures. The memory system. The AndueCore5 separates instruction storage and data storage. Program instructions are stored in instruction memory. This memory contains the sequence of operations that the processor executes. Data ROM stores constant values that programs can use during execution. These values can represent numbers, addresses, display information, or other stored information. Data ROM can transfer information to the bus register, program counter, or stack memory. This separation allows programs to contain both instructions and stored data without requiring the processor to generate values manually. The stack system. The stack is a flexible memory structure controlled by the stack pointer. The stack pointer identifies which memory location is currently selected. The processor can move through stack locations using stack pointer increment and stack pointer decrement instructions. Data can be written into the stack from the bus register. This allows programs to store temporary information, save values, and create persistent states. Data can also be read from the stack back onto the bus register. This allows previously stored information to return to the main data path. One of the unique design choices of the AndueCore5 is that the stack is also used as graphics memory. Instead of creating a completely separate graphics memory system, the processor reuses the existing stack architecture to store display information. This reduces hardware complexity while increasing the usefulness of the memory system. The stack therefore serves two roles. It acts as general-purpose memory for programs and also acts as the storage system for the display hardware. This shared design philosophy is one of the defining characteristics of the AndueCore5. AndueCore5 display system, input systems, and instruction operation. The display system of the AndueCore5 is one of the most unique features of the architecture. Instead of treating graphics as a separate device controlled by software, the display is directly integrated into the processor design. The same memory system used for storing information can also be used to create visual output. The display system is based around 3 independent 5 by 5 frame buffers. Each frame represents a complete 5 by 5 pixel image. These frames allow the computer to store multiple images at the same time and switch between them without requiring the image data to be rewritten. Each frame can contain a different picture, animation frame, or word. The processor can select which frame is currently displayed through dedicated frame control instructions. The frame system allows the AndueCore5 to create simple animations by storing multiple images and cycling between them. Instead of a program constantly rebuilding a picture, the hardware can simply switch between stored frames. This creates efficient animation while minimizing processor workload. The bitmap display mode. In bitmap mode, the display interprets stored values as pixel information. Each value represents a row of pixels within the 5 by 5 display. A complete image is created by combining the stored rows together. Each pixel can either be active or inactive, allowing the processor to create shapes, symbols, patterns, and simple animations. Because the display is based on stored frame data, programs can create graphics by changing memory values rather than directly controlling individual pixels. This approach is similar to the way real computers use frame buffers. The image exists as stored data, and the display hardware converts that data into a visible output. The character display system. The AndueCore5 also contains a character display mode. This allows the same display hardware to be used for text output. When the character display toggle instruction is activated, the display changes from bitmap interpretation to character interpretation. Instead of treating the stored values as pixel rows, the display logic interprets each stored value as a character code. The character system uses a simple alphabetical encoding. The value 1 represents the letter. The value 2 represents the letter B. The value 3 represents the letter C. This continues sequentially until the value 26 represents the letter Z. Each frame can therefore contain 5 character values, allowing the processor to display a 5-character word. Because the system contains 3 independent frames, the computer can store 3 separate words at the same time. A program can manually choose which word to display or enable automatic cycling to display multiple messages. This creates a simple text display system without requiring a large character memory or complex graphics hardware. The relationship between graphics and text. One of the important design principles of the AndueCore5 is hardware reuse. The bitmap display and character display do not use separate memory systems. They both rely on the same frame storage. The difference is only how the stored information is interpreted. In bitmap mode, values represent pixels. In character mode, values represent letters. This demonstrates an important concept in computer architecture. The same physical data can represent different information depending on how the hardware interprets it. The random number generator. The AndueCore5 contains a hardware random number generator based on a continuously running 5-bit counter. The counter operates independently from normal program execution. It is always changing and provides a constantly changing source of values. When the random number instruction is executed, the current counter value is captured and placed onto the bus register. The counter is paused during the capture operation, allowing the program to receive a stable value. This system provides a simple method for creating unpredictable behavior. The random number generator can be used for games, simulations, procedural effects, and any program requiring variation. Because the generator is implemented as hardware rather than software, it requires no additional calculation instructions. Instruction set theory of operation. The instruction set of the AndueCore5 is designed around direct hardware control. Each instruction represents a physical operation performed by the machine. Rather than using complex instructions that perform many tasks at once, the architecture uses simple instructions that can be combined to create more advanced behavior. This design philosophy mirrors early computer systems where programmers controlled hardware by carefully arranging simple operations. Null instruction. The null instruction performs no operation. It exists as an empty instruction that allows unused memory locations to remain harmless. It also provides future expansion space for additional features. Load read instruction. The load read instruction transfers the current value stored in the bus register into the read register. After the transfer, the bus register is cleared. This instruction allows programs to place a value into the first arithmetic input register. Load green instruction. The load green instruction transfers the current value stored in the bus register into the green register. After the transfer, the bus register is cleared. This instruction allows programs to place a value into the second arithmetic input register. Red-green instruction. The red-green instruction copies the current value stored in the green register onto the bus register. The green register remains unchanged. This allows a stored value to be reused multiple times without reloading it from memory. Red arithmetic logic unit instruction. The red arithmetic logic unit instruction copies the current arithmetic result onto the bus register. The arithmetic logic unit continues operating normally, and the red and green registers remain unchanged. This instruction allows programs to capture calculations and move results to other parts of the system. Subtract toggle instruction. The subtract toggle instruction changes the arithmetic logic unit between addition and subtraction modes. When subtraction mode is active, the arithmetic logic unit calculates the difference between the red and green registers. When subtraction mode is inactive, the arithmetic logic unit performs addition. The toggle remains active until changed again. Reserved instruction. One instruction location is reserved for future expansion. Currently, it performs no operation. Load program counter instruction. The load program counter instruction copies the value currently stored on the bus register into the program counter. This creates an unconditional jump. Program execution continues from the new address. Hold instruction. The halt instruction pauses processor execution. The machine remains stopped until the user clears the halt state. This instruction is useful for demonstrations, testing, and programs that intentionally stop after completing a task. Data ROM to bus instruction. The data ROM to bus instruction reads a value from data memory and places it onto the bus register. The address used is based on the current program counter location. This allows programs to retrieve stored constants and data. Data ROM to program counter instruction. The data ROM to program counter instruction reads a value from data memory and places it directly into the program counter. This creates an indirect jump. The destination address is stored in memory rather than directly provided by the program. Data ROM to stack instruction. The data ROM to stack instruction transfers stored data directly from data memory into the current stack location. This allows programs to initialize stack memory with stored values. Stack pointer increment instruction. The stack pointer increment instruction moves the selected stack location forward. This allows programs to move through stack memory. Stack pointer decrement instruction. The stack pointer decrement instruction moves the selected stack location backward. This allows programs to access previous stack locations. Bus to stack instruction. The bus to stack instruction writes the current bus value into the selected stack location. This stores information in memory. Stack to bus instruction. The stack to bus instruction reads the selected stack location and places its value onto the bus register. The stored stack value remains unchanged. Frame control instructions. The frame control instructions select which display frame is active. Frame 1 toggle selects the first frame. Frame 2 toggle selects the second frame. Frame 3 toggle selects the third frame. Frame cycle toggle enables or disables automatic cycling between frames. These instructions allow programs to control graphics and animation. Bus to output instruction. The bus to output instruction transfers the current bus value into the output register. After the transfer, the bus register is cleared. This provides a method for sending calculated values to external displays or output hardware. Jump if overflow instruction. The jump if overflow instruction checks the overflow state of the arithmetic logic unit. If overflow is active, the processor loads a new program address from data memory. If overflow is inactive, execution continues normally. Jump if zero instruction. The jump if zero instruction checks whether the arithmetic logic unit output is completely zero. If the result is zero, the processor performs a conditional jump. This provides comparison and decision-making ability. Random number instruction. The random number instruction captures the current value of the hardware random number generator and places it onto the bus register. +1 instruction. The +1 instruction adds 1 to the current arithmetic result by activating the carry input. This provides an efficient method for creating counters and incrementing values. Character display toggle instruction. The character display toggle instruction enables or disables character interpretation mode. When enabled, stored values are converted into letters. When disabled, stored values are displayed as pixels. This instruction allows the same hardware to support both graphics and text. AndueCore5 programming theory, software design, and system capabilities. The AndueCore5 is designed around the idea that a computer does not need a large instruction set to become powerful. The ability of a computer comes from the interaction between simple instructions. Each instruction performs one specific hardware operation, but when many instructions are combined together, they create complex behavior. This is the same fundamental principle used by all computers. Simple operations performed at extremely high speed allow machines to perform tasks that appear much more complicated. The AndueCore5 demonstrates this concept in a way where every operation can be observed and understood. Programs for the AndueCore5 are created by arranging instructions in memory. Each instruction tells the hardware what action should occur next. Because every instruction directly controls hardware, programming the machine requires an understanding of how information moves through the architecture. A programmer must think about where information is stored, where it needs to go, and which instruction will perform the required transfer. This creates a close relationship between hardware design and software design. Unlike modern computers, where software is separated from the physical processor, the AndueCore5 creates a direct connection between programming and hardware operation. A program begins execution when the program counter points to the first instruction. The processor reads that instruction, performs the requested action, and moves to the next instruction. This continues until the program reaches a halt instruction or changes execution flow using a jump. Loops are created by changing the program counter back to an earlier instruction location. This allows the processor to repeat sections of code indefinitely or until a condition becomes true. Conditional logic is created by combining arithmetic operations with conditional jumps. For example, to compare two values, a program can load one value into the red register and another value into the green register. The subtraction toggle can then be activated. If both values are equal, the arithmetic logic unit produces 0. The jump, if 0 instruction, can detect this condition and change the program flow. This simple combination of subtraction and 0 detection creates the foundation for many higher-level programming concepts. The AndueCore5 does not require a dedicated comparison instruction because comparison naturally emerges from the behavior of the arithmetic logic unit. Game design on the AndueCore5. One of the most interesting applications of the architecture is creating simple games. Because the processor contains memory, arithmetic, conditional logic, random numbers, and graphics output, it can create interactive experiences. A guessing game is a good example. The random number generator can produce a hidden value. The player provides guesses through an input system. The processor compares the guess with the stored value using subtraction and 0 detection. If the guess is correct, the program branches to a winning sequence. If the guess is incorrect, the program can continue and allow additional attempts. The processor does not need a special game instruction. The game exists entirely because simple hardware operations can be combined into a larger system of logic. Other possible games include number challenges, reaction games, memory games, and simple animated displays. Graphics programming. The graphics system of the AndueCore5 allows programs to create images by controlling stored display data. Because the display uses frame memory, a program can prepare an image before showing it. This allows smooth animation because the processor can switch between completed frames rather than rebuilding an image while it is visible. A program can store several different images in the available frames and use frame cycling to create movement. For example, a simple character animation can be created by storing several versions of a character and switching between them repeatedly. This approach demonstrates the same basic idea used by larger computers that use frame buffers for graphics. Text display programming. The character display system provides another method of communication. Instead of drawing each letter as a bitmap, the processor can store character values and allow the hardware to decode them. Because each frame stores 5 characters, programs can create short messages, labels, and status displays. The 3-frame system allows multiple messages to exist at the same time. A program could store a title screen in one frame, a score display in another frame, and a game message in the 3rd frame. The frame selection system allows the program to decide which information is currently visible. The importance of hardware reuse. One of the strongest design principles of the AndueCore5 is hardware reuse. The architecture avoids creating separate systems when existing hardware can be adapted. The stack is both memory storage and display storage. The arithmetic logic unit is both a calculator and a comparison system. The same frame memory is both graphics storage and character storage. The bus is both a data pathway and a communication system between every major component. This approach allows the computer to achieve more functionality while remaining within the strict construction limits of No Man's Sky. Building inside No Man's Sky. Creating the AndueCore5 inside No Man's Sky introduced unique engineering challenges. Unlike a traditional computer built from manufactured components, the entire machine had to exist within the limitations of a game-building system. Every logic gate, every switch, every connection, and every display element required physical construction space. The project had to balance complexity with efficiency because every added feature consumed part capacity. Reaching the maximum construction part limit required careful optimization. Unnecessary structures had to be removed, and each remaining component had to serve a useful purpose. The final system operates reliably at the maximum part capacity without relying on glitches or unstable behavior. This is an important achievement because the machine is not simply large, it is functional. The challenge was not only creating individual circuits, but integrating thousands of components into a single coordinated system. The result is a complete programmable computer existing entirely within a game environment. Engineering philosophy. The AndueCore5 follows several important engineering principles. The first principle is simplicity. Every component should have a clear purpose. Complicated behavior should emerge from combining simple systems rather than creating unnecessary complexity. The second principle is transparency. The operation of the machine should be understandable. A person should be able to examine the hardware and understand how data moves and how instructions affect the system. The third principle is modularity. Each subsystem should function independently while still integrating with the larger computer. The fourth principle is expansion. The architecture should allow additional capabilities to be added without destroying the existing design. The fifth principle is efficiency. Because the computer exists within No Man's Sky, every component matters. The design must achieve maximum capability while using limited resources. The future of the architecture. The AndueCore5 is designed as an evolving platform. Additional instructions, display features, memory improvements, and hardware expansions can be added as new ideas are developed. Possible future expansions include more advanced graphics systems, additional input methods, expanded memory systems, more complex games, and additional programming capabilities. However, future improvements must continue following the original design philosophy. The goal is not simply to make the computer larger. The goal is to make the computer more capable while preserving understanding and simplicity. The achievement of the AndueCore5 is not measured by speed or size. It is measured by the fact that a complete programmable computer was created from basic logic inside a game environment. The project demonstrates that the fundamental ideas of computer science can be explored anywhere, even inside a virtual world. The AndueCore5 represents the connection between digital logic, engineering creativity, and programming theory. It is a physical demonstration of how simple components can be combined into a machine capable of storing information, performing calculations, making decisions, generating output, and executing programs. At its core, the AndueCore5 proves one fundamental idea. A computer is not defined by its complexity. A computer is defined by the ability to represent information, manipulate that information, and follow instructions to create meaningful results. AndueCore5 Complete Technical Reference and Operational Theory. The AndueCore5 represents a complete computer system built from the fundamental concepts of digital logic. Although the architecture is intentionally small compared to modern computers, it contains every major element required for programmable computation. It contains memory, processing, control flow, input generation, output capability, and a method for storing and displaying information. The design demonstrates that the essential ideas behind computing are not dependent on large-scale hardware. The same principles found in modern processors exist in simplified form within the AndueCore5. Information is stored as binary states. Instructions control hardware behavior. Arithmetic circuits transform data. Memory preserves information. Control logic determines the order of operations. The central concept behind the architecture is that computation is the controlled movement and transformation of information. Every instruction executed by the processor changes the state of the machine. A state change may involve moving data into a register, changing the arithmetic mode, modifying the program counter, updating memory, or changing what appears on the display. The computer does not understand numbers, letters, pictures, or games. It only understands electrical states represented as binary values. Meaning is created by the way the hardware interprets those values. A stored value can represent a number during a calculation, a character during text display, a pixel pattern during graphics mode, or an address during program execution. The hardware determines the meaning of information based on the current operation. This concept is one of the most important ideas demonstrated by the AndueCore5. Data is not inherently meaningful. Meaning comes from interpretation. The control system. The control system is responsible for coordinating every operation performed by the processor. When an instruction is fetched, the instruction decoder determines which hardware components should activate. The decoder acts as the connection between the programs stored in memory and the physical hardware. An instruction does not perform work by itself. Instead, it activates signals that allow specific hardware actions to occur. For example, the load red instruction does not calculate anything. It simply activates the path that allows the bus register value to enter the red register. The red-green instruction activates the path that allows the green register value to become available on the bus. The subtract toggle instruction changes the state of the arithmetic logic unit control system. The frame instructions modify the display control system. Each instruction is therefore a command to the hardware. The processor is not interpreting instructions like a human would. It is responding to patterns of control signals generated by the decoder. This is the foundation of processor design. Memory organization. The AndueCore5 uses multiple forms of memory because each type serves a different purpose. Program memory stores the instructions that tell the computer what actions to perform. Data memory stores information that programs need while running. Stack memory stores temporary values and also provides storage for the display system. Each memory type exists because the processor requires different ways to organize information. Program memory provides sequence. Data memory provides stored values. Stack memory provides flexible temporary storage. Together, these systems allow programs to become more than simple sequences of commands. The stack architecture. The stack system is an important part of the AndueCore5 because it provides flexible storage while also supporting graphics. The stack pointer determines which stack location is currently active. By moving the stack pointer, the processor can access different stored values. Values can be pushed into memory from the bus. Values can be retrieved from memory back onto the bus. This creates a simple but powerful storage system. The stack can store calculations, program data, display information, animation frames, or any other information a program requires. Because the display system uses stacked memory, the architecture avoids the need for a completely separate graphics memory system. This is an example of efficient hardware design. A single subsystem performs multiple functions while keeping the architecture understandable. Arithmetic operations. The arithmetic system is intentionally simple. The processor does not contain many specialized mathematical instructions. Instead, it relies on the arithmetic logic unit and the ability to combine instructions. Addition is performed using the standard operation of the ripple carry adder. Subtraction is achieved by changing the behavior of the adder through the subtraction toggle. Incrementing values is achieved through the +1 instruction. Complex calculations are created by repeating simple operations. This reflects how early computers were designed. Rather than containing an instruction for every possible calculation, they provided a small set of fundamental operations that programmers could combine. Comparison operations. The ability to compare values is essential for programming. The AndueCore5 creates comparisons through subtraction. When two values are placed into the arithmetic logic unit and subtraction is enabled, the processor effectively asks whether the two values are equal. If the answer is yes, the result becomes 0. The jump if 0 instruction can detect this condition and change the program flow. This simple mechanism allows the processor to create decisions. Decisions allow programs to respond to conditions. Conditions allow programs to create games, simulations, and interactive behavior. Display operation. The display system demonstrates how stored information can become a visual output. The processor does not directly create an image. Instead, it creates data that the display hardware interprets. In bitmap mode, the stored values represent pixel information. In character mode, the stored values represent letters. The display hardware converts these stored states into visible information. This separation between data and presentation is a fundamental concept used throughout computer graphics. Program examples. A simple counter program demonstrates the architecture. The program stores an initial value. The value is placed into the arithmetic logic unit. The +1 instruction increases the value. The output system displays the result. The program repeats by jumping back to the beginning. From a small collection of instructions, the processor creates a continuously updating display. A simple animation program demonstrates the frame system. Several images are stored in different display frames. The frame cycle system is enabled. The display automatically switches between frames. The result is motion created entirely by stored hardware states. A text display program demonstrates character mode. Character values are stored in frame memory. The character display mode is enabled. The display hardware converts the values into letters. The result is a message produced by the computer. These examples show that advanced behavior does not require advanced instructions. It requires combining simple instructions in creative ways. Engineering achievement inside No Man's Sky. The creation of the AndueCore5 inside No Man's Sky presents a unique engineering challenge because the environment was never designed to function as a computer construction platform. Every component must exist within the rules of the game. Every connection must be physically constructed. Every subsystem must operate using available building mechanics. The project required solving problems that do not exist in traditional computer engineering. Hardware efficiency became a major design requirement. Adding a feature was not simply a matter of adding more components. Every addition consumed limited construction capacity. Therefore, every design decision required balancing capability against resource usage. The final computer operates at the maximum part limit while remaining stable. The machine does not rely on glitches. It does not depend on corrupted game behavior. It operates using intended building mechanics and logical systems. This makes the project a demonstration not only of computer architecture, but also of engineering optimization. The AndueCore5 shows that complex systems can emerge from simple rules when those rules are carefully organized.